this next section, we're going to be looking at the fundamental theorem of calculus. And what this is going to allow us to do is it's going to allow us to calculate the area under the curve using an integral. And it's going to allow us to solve integrals with numbers in them. Now, the fundamental theorem is essentially the following. Here, little f is some function, and big F is the integral of that function. So f prime, big F prime, is equal to little f. So what you do is, if you want to do this integral from a to b, where here a and b are numbers, what you do is you integrate little f of x to get big F of x, and then you plug in b, the top, and then you plug in a, the bottom, and you take the difference. And usually there's a step that we write in between here, which is a notation step, and usually it works like this. We take the integral from a to b of little f of x dx. We integrate that and we get big F of x, and then we draw this big vertical line and we put an a at the bottom, number, whatever it is, and the other number at the top. And then you plug in. You take the b and you put it in there. And you take the a and you put it in there, and you take the difference. And it's always the top minus the bottom. And that's how all these integrals are going to work. So you have one additional step to what you were integrating before, and that's plugging in the numbers. So let's look at our first example. Here we have the integral from 2 to 10 of the quantity 2x plus 3. If we integrate, what we're going to do is the integral of 2x is 2x squared divided by 2. The integral of 3 is 3x. Now normally what we would do is we would add c to this, but when you do a definite integral, when you're plugging in these numbers, you don't need the c. You can pick c to be whatever you want, and we're going to pick c to be 0 for these. And I'm going to evaluate that from 2 to 10. And so what we do is we take and we plug in the top, put that in for x, and so the 2's of course cancel. I'll cancel them in red, and we get a 1. So we get 10 squared plus 3 times 10 minus, and then we plug in the 2 for x and x, and we get 2 squared plus 3 times 2. And so then a little bit of arithmetic. Let's see, 100 plus 30 minus, that's going to be 4 plus 6 is 10. So the answer is 120. And that is the area under the curve of 2x plus 3 from 2 to 10. I'm going to draw that as a picture. This is still example 1. So if you take 2x plus 3 from 2 to 10, now you don't have to do this every time. I'm just doing this to illustrate what we just did. So let's see. 2 and let's say 10. So here's 3. If you plug in a 2, you get 7. And if you plug in 10, you get 23. It's right there. And so what we were calculating was the area under the curve. And that area is really the area of a trapezoid. The average of the two heights times the length of the base. Or the average of the two bases times the height, depending on how you want to look at this. And so that's 7 plus 23 divided by 2 times 8, and that is equal to 120, which is exactly what we said the area was. And I'm just going to draw that area equation for you here. It's 1/2 the average of the bases times the height. That's for a trapezoid that looks like that. So, at least for a straight line, the formula works, and it actually turns out that it works for all shapes. Now, they're not all polynomials. Sometimes you have something here like y squared and e to the y, and this is all integrated with respect to y, but the procedure is still the same. You integrate, and so you get y cubed over 3. The integral of e to the y is e to the y, and I evaluate from 0 to -3. Same story, plug in the top, -3 first, and I'm going to do it down here. So I get -3 cubed over 3 plus e to the -3, that's top, minus the bottom. And here, do be careful because e to the 0 is 1. And so you get -9 plus e to the -3 minus 1 is equal to -10 plus e to the -3. So no matter how complicated your expression is, it still works the same way. You integrate, you plug in the top, you plug in the bottom, and you take the difference. Here's another one. Whoops, too far. For this one, we have the integral from 1 to 2 of 8 minus 4x cubed, and we're going to integrate that again. 8x minus 4x to the 4th over 4, and we evaluate that from 1 to 2. Now if you want to, you can rewrite that 8x minus x to the 4th from 1 to 2. And you plug in the top into the x's, and you get 8 times 2 minus 2 to the 4th minus 8 minus 1, because you plug in the 1. And when you work all that out, you end up with -7. but the procedure is still the same. Take the integral, plug in the top, plug in the bottom, take the difference. Now for this next problem, what we have is we have this 12 over t. And so what I'm going to do is this 12, I don't really want to have that inside the integral because I'd like to integrate this as natural log. So what I'm going to do is I'm going to rewrite this. I'm going to take the 12 out front. I'm going to integrate from minus 2 to minus 1 of 1 over t dt. And this integral is the natural log of t. And usually if we have this absolute value here, we don't write two vertical lines. We just evaluate it from minus 2 to minus 1. But the story is still the same. You plug in the top, minus 1, and you plug in the bottom, minus 2. And so you get 12 times the natural log, and the absolute value of minus 1 is 1, minus 12 times the natural log of 2. Now, the natural log of 1 is 0, which means all we're left with is negative 12 times the natural log of 2. The natural log integrals are probably the hardest because what you have on the left, 1 over t, doesn't look like what you have on the right, natural log of t, whereas for all our other integrals, they do look at least similar. But this is just one of those you have to memorize. Now, here it says find the area of the region under the graph of the function f on the interval a to b. And here we have a function, it's 2x plus 3 on minus 1 to 2. Now, when you want to find the area of the region, all you have to do is take the integral. That's the integral from a to b of f of x. The only difference between this problem and the previous ones is that you don't have the integral set up for you. You have to write it down yourself. So the area is going to be the integral from negative 1 to 2 of 2x plus 3 dx. And so if we integrate that, x squared plus 3x from negative 1 to 2. You put in the top. Let's see what we put here. 2 squared is 4, plus 3 times 2 is 6. Top. Put in the bottom. Minus 1 squared, should have done that. That's 1. And 3 times negative 1 is negative 3. And when you work all that out, you get, what do we have there? 10 plus 2 is 12. So if you're asked for the area of the region, you simply take the integral across your interval. Here's another one, and once again, I have 1 over x, so that's going to have some items in the denominator, that's going to have the x in the denominator, and when I integrate that, I'm going to end up with natural log. But this works very similar. Take the integral from 1 to 2 of 1 over x dx, and when you integrate that, you have the natural log of the absolute value of x from 1 to 2. Now in this case we didn't need the absolute value because both 1 and 2 are positive, but it doesn't hurt. So we have the natural log of 2, that's top, minus the natural log of 1, that's the bottom, The natural log of 1 is still 0. And so all we're left with here is the natural log of 2. So all of these area under the curve and evaluating what we call a definite integral. We say it's a definite integral because it has a number answer. They always work the same. You integrate, plug in the x value at the top, plug in the value at the bottom, take the difference. And that concludes the section on integration, definite integrals.